Now, what he did for science, well, he definitely did a lot of study within the relevance entropy, right, within that of a closed system, right, because that's the only way it can be done, right? It is a specialty which requires a level of complexity which is incorporated into a system. Now, Hawking, he definitely contributed to the analyzation of radiation, in which that was contributed to that on land, reading it from the sun or reading it in space. You know, his equations were definitely a great way to solve, you know, radiation in its problem. Now, were those equations great? Well, they're not theories, right? That's a start. Okay.
Right. So I would say it's really Stephen and also Jacob Bekenstein.
Yes, absolutely.
There we go. Bekenstein radiation, Hawking
Yeah.
radiation. There we go. Bekenstein.
So the idea
Birkenstein.
was, what happens if you take a
Hawking
black hole, which,
Birkenstein
I would
radiation.
say they
Yeah,
were
blah, blah,
still
blah.
mysterious as
We do this.
classical objects
We
in
all
the early
know
70s, but
this.
much less
We're all
mysterious than they had been.
at this point. If you've been watching enough, that you've done enough of these fucking science things with me, you're basically a fucking astrophysicist by this point. You've basically got a bachelor's in science at this point. You just got to do the refining. I recommend Khan Academy.
In previous decades, there was a sense that you can actually make a black hole from gravitational collapse, that in fact a black hole is in some sense perhaps the generic outcome of that gravitational collapse due to the Penrose theorem. And so there was some sense of, okay, well, let's now finally start to think about what happens when we start to include quantum mechanics. And from the point of view of quantum mechanics, the black hole is a very mysterious object because you throw things in and nothing comes out classically. Any information about how you made the black hole, what you made it out of, is almost completely gone. It's not quite completely gone because there's the mass and the charge and the angular momentum, which are left over. So there are a few basic conserved quantities about how you made it that are left over. But everything else, when you threw in a diary, what was written in the diary, did you make it out of photons, or did you make it out of neutrinos, this kind of question, or did you make it out of gravitons? All of that seems to be gone. Whereas in quantum mechanics, the laws of physics are invertible. So if you can run them forward in time, you can run them backward in time. If you know the state of the universe today, you can evolve forward to know the state of the universe tomorrow. And also, if you know the state of the universe tomorrow, you can evolve it back to find out what was the state of the universe today. That's a very fundamental part of quantum mechanics, and it seems to be in tension with the basic structure of a black hole, which is that you throw stuff into the hole and it just stays there, it doesn't come out. And so Hawking was trying to get at that tension by seeing what happens when you make black holes quantum mechanical. Now, he had a big problem in doing that, however, which is that he didn't have a theory of quantum gravity. He knew that there was general relativity, Einstein's beautiful classical theory of gravity. He knew about quantum mechanics and really quantum field theory as a theory of the fundamental microscopic forces, not including gravity.
Oh well, all right. He's definitely touched on a lot of things, I guess, passionate, but it would have been nice for having him highlight his overall things first. But